Yes.
Okay. And then how do I do the pointer? Okay, so I'm going to try to point with the computer. Well, we'll see what happens. All right. So first of all, thanks very much. I'm Karl Berggren. I'm from MIT, Electrical Engineering Department. I'm going to talk about computing with superconducting nanowires. So the talk is really about the technology, the computing part of it. I hope people who are listening will think about it in the context of their own applications and maybe can think of some very cool things to do with this technology. So first of all, I'm going to start with the Josephson junction. So the Josephson junction is the core technology of the qubits. They're the core technology of, if you've heard of it, SFQ electronics, which is the superconducting classical electronics family. They're the core technology of the SQUID, which is the best magnetic field sensor out there. And they're basically the start of all superconducting devices. And they're fascinating because they start with a superconductor, a normal material that's very thin enough so that the quantum wave function of the electrons can actually jump across it without dissipating any power. And so you have basically a resistor, this insulator that's acting like a superconductor. And it can be modeled to make electrical engineers happy as a capacitor, a resistor, and this device, which is essentially a programmable inductor. It's an inductor whose inductance varies with the bias current. Okay, and you can call it an ideal Josephson junction, maybe, but really this whole thing is the Josephson junction. An IV curve, it looks a little bit like a voltage regulator or a diode in parts. It looks like resistor in parts. And in this part, it looks like a superconductor. It has a no voltage appearing on it because there's no resistance in a superconductor. I mean, you can also visualize it as a physical system. So it's often thought of as containing a pseudopotential related to the energy in the device. And the x-axis here is the phase, which is basically the flux. It's the integral of the voltage on the device. And the Josephson junction canonically makes this kind of washboard potential shape. And you can change that shape with the current that goes through it. So you have a knob with which you can turn this device. And you can use topology, like making loops, to create much more interesting constraints on the system. You can add Josephson junctions with these devices to make multi-dimensional potential landscapes. And so you can do things. So this is the core technology behind the quantum computers. They're taking advantage of these kinds of complex nonlinearities. They have a lot of great things about them. They're incredibly fast. So the plasma frequencies can be up there at 100 gigahertz. So you can do electronics at 20 gigahertz and everyone's happy. And they're very low energy dissipation, less than, 0.1 attojoules per switching event, which is, 1/10,000th or 100,000th of what CMOS can do. And the physics is very interesting. There are also some bad things about Josephson junctions. And the first is that their physics is very interesting. And in fact, if you look at the history of this technology, there were alternatives being explored. But as soon as the Josephson junction came along, the entire physics community really focused in on it. And the electrical engineers who were developing in more traditional devices kind of lost momentum. And since then, we've had maybe 60 years of development of this technology, and some amazing things have happened. I'm going to rewind a little bit and sort of tell you the story about a technology that kind of lost its way. The other disadvantage of the fabrication of the materials is quite limited. So we heard about aluminum oxide. That's a beautiful Josephson junction. A niobium aluminum oxide. We don't have that amazing oxide interface that CMOS has. It's just self-passivated, terminated, and beautiful. And also, they're only one device. We don't have diodes. We don't have BJTs, bipolar transistors. We don't have thyristors, a little callback to an earlier talk there. But anyway, so we need sort of some of these other technologies. And one other one is that they have very low input and output impedance. So they're great for power transfer between Josephson junctions. If you want to transfer power output impedance of 1 ohm to an input impedance of 1 ohm, you can do that, but they're not very good if you want to try to drive a CMOS gate, an LED, or something like that. All right, so let's start with the alternative. So this is just a superconducting wire. It's basically just 3 microns thick, and this is where the action happens. 200 nanometers thick. You can make them thinner, you can make them less thick. It's not really, the size isn't critical. It has a similar IV characteristic. It has a region here with 0 voltage in it, the superconducting region. If you overdrive this thing, excuse me, you overdrive this thing, it switches into a normal state. Just a hot spot of metal appears. No coherence, there's no tunneling across it of a quantum wave function or anything like that. Superconductor, resistor, superconductor. That due to the thermal physics of it, that's self-stabilizing. And so it ends up having this sort of interesting flat current source-like IV characteristic. If you heat it up even more, of course, the whole wire becomes normal, and now you just have a resistor. So it's got a very simple IV characteristic that one can model using classical physics. It's actually analogous to a device. It is basically a device that was developed in the 1960s by Roderick and Room, right before the Josephson junction was invented, called a callitron. So callitron was the device where you hit it with a current pulse, the ignition pulse, that puts you over the top of that superconducting branch, at which point you have to switch into this normal state. That latched into the normal state. You could hold that normal state until you had a negative going pulse that would unlatch you from that state. That's a dual to the modern semiconductor device, the diac, which is a form of a thyristor. And just because thyristors came up yesterday in a slightly sort of old-fashioned context, we'll say in their defense, if you go to New York today and you have enough money, you can buy 241,000 of them. They're in stock. So these are useful devices, okay? They're not useful for your cell phone, but for the lights and that projector and for everything around us that's keeping us warm and illuminated. These are critical devices, okay? And that's a little bit what I'm trying to say, is that we can't just have the Josephson junction and figure it's going to solve all of the problems that we're facing, okay? So what are the devices? So in the Middle Ages, people imagined all kinds of monsters and they would make books filled with them. So here's my bestiary, my book of monsters, okay? So that's a basilisk if anyone's interested. Right, so the first one I've already talked about is a constriction. One I'll talk about next is a superconducting nanowire single photon detector. It's just like a constriction. Instead of applying a current pulse to latch the device, actually use a photon to latch the device. These are tremendously useful devices. They're used in topics ranging from quantum computing, space communications, and they're basically a wire. The physics of them is just what I showed you before. It's got the same IV characteristic, but they're sensitive to single photons, especially single infrared photons. They give you a nice voltage pulse, a few hundred millivolts if you amplify it. So you can stick it onto a room temperature amplifier, an oscilloscope, and you can get a 5 nanosecond wide pulse telling you if a photon was absorbed. Has a number of useful electronic properties. First of all, they're sensitive. Actually, now JPL just released a paper that goes out to 29 microns infrared wavelength. They have jitter, which is the timing and accuracy of about 3 picoseconds. They reset in a couple nanoseconds. They have a dark count, which is like a false event rate, less than 1 per day. And they're quite convenient to work with. They are cold. You need to be at a few Kelvin, but not, quantum computing cold. They're not like 10 millikelvin. So they can be worked with reasonably effectively. Okay, another of our beasts is the heatertron. So this is basically a thermal relay. Instead of a photon switching the device, just use a burst of heat to switch the device. So imagine instead of biasing it, that we exceed the critical current here, we actually suppress the critical current with some heat. Okay, that's the core idea. And we draw it like this. Actually, one of the fun things is we've gotten to invent a bunch of our own circuit symbols. So that was, we got a heater here. We have this gate. The heater transfers energy to the gate. You get a decent gain characteristic here, about a factor of differential gain of about a factor of 5. There's plenty to do logic with and build small computers and things like that. Another one we call the nanocryotron, which is a device that has a direct galvanic connection. So you just shove current into the channel. This was developed by my student Adam McCon. And basically, when the gate switches, so the gate eventually, you put enough current in the gate, it switches, and the heat from the gate will go across here so that any current coming down the channel gets pushed into the resistor. And so you can make an inverting amplifier. If you can make an inverting amplifier, you can make basically anything. That device switches, it goes across the channel, you get some joule heating in the channel, and now you can have a nice 100 ohm, kind of impedance drive into whatever you want with it. So that has an amazing differential gain. It's basically infinite, at least at low frequencies. So yeah, we were able to build electronics with that as well. All right. Last one is a Ytron. I'll kind of skip this. If anyone wants to talk about it, it's kind of got cool physics, so we'll try not to get too excited here. But it's basically a device that if you have the same amount of current, then everything's nice and sort of laminar here. Nothing happens. But if you take the current away from one arm, current crowds, tries to get a shortcut, and that crowding causes the device to switch. So you can have a sort of negative, you remove the current and the device switches. Okay, so what can you do with this? You can do logic circuits. So here's an example of a half adder that we made, which had, I think, about 15 gates in it. Sorry, it's about 10 gates. It's about 15 trons in it. And if you can add in binary, you can verify that this device works. We've since then developed the technology. So this is another one of my students, Matteo Castellani, developed this. This is a pretty sophisticated device. It's a 2-digit counter that is counting photons that are being absorbed by a single photon detector. So right here we have single photon detector on the same chip. Then you have signal being fed into one of our trons. When the tron fires, it develops a voltage here that dumps some flux, magnetic, well, not magnetic. Okay, we'll talk about that in a second. Dumps flux. What kind of flux I'll specify. Into this loop. And this loop does not have enough current as a result to trigger the next tron. When the second photon arrives, this device spikes again, adds to the current, and now there's enough current to trigger the second tron, and the second tron fires. And this process can be repeated, so you can count in base 2, you can count in base 3 with this device. And very kind of proud of this because this is an actual margin analysis of the device telling us that it has margin. So plus or minus 10% bias current, plus or minus 10% bias current, and you can get a large region with very low error rates in this device. So it can also count in base 3, although with reduced margins. Yeah.
Like you have a on-demand single photon source?
No, we just shine light in there, and this is visible light or infrared light comes in, it hits one of these wires, makes the wire switch. Now that pulse travels into here. We hit it with a laser spot with hundreds of photons in it, but only one is absorbed. Okay. We can verify that through power scaling and things like that. We can verify that we're only absorbing one of them.
Okay, that's
Yeah.
one.
Sure. Okay. So you remember I kind of fumbled when I talked about flux. So in a superconducting loop, famously in the squid, what happens is that the magnetic field in the loop induces a current, and that is what's sensed. And in most superconductors, that's the right way to think about it. In these superconductors, they're very thin. They have a very large magnetic penetration length, much, much longer than their thickness. As a result, they have very few charge carriers. So the Cooper pairs famously are the charge carriers for superconductor. Here we have one maybe there's a few thousand charge carriers per cross-sectional area of the device, micron length. I'm sure that number's wrong, but it's small. It's like one charge carrier, like 10 charge carriers per cubic nanometer. That's the number. And as a result, carry 100 microamps, these charge carriers have to move very fast. So whereas the drift velocity in silicon might be, I don't know, a centimeter per second or less, in these systems, it's like 10 meters per second. It's like an Olympic sprinter speeds, okay? And as a result, that velocity is squared when you think about the kinetic energy. So the kinetic energy of the charge carriers in these devices is absolutely enormous. It dominates that inertial inductance called kinetic inductance, dominates by a factor of 1,000 over any magnetic effect. So in superconductivity, we call this fluxoid, and then we forget that and we just call it flux. But what's in here is fluxoid, not flux. So just keep that in mind. There's not a lot of actual magnetic field in there. Right. So microwave electronics. So because of that high kinetic inductance, effective magnetic permeability of the device is enormous. It's like 300 mu naught or something like that, much, much higher than like ambient magnetic fields. It's really like a pseudo-magnetic material. And as a result, if you make a transmission line with it, the characteristic impedance of that transmission line is huge. It's kiloohms. The effective velocity is tiny. It's like 1% or less of the speed of light. The effective wavelength is tiny. It's like 1% or less of the wavelength of the microwave. Instead of having a microwave we heard in the last talk, the 10 gigahertz resonator was about a centimeter size, you can now make that resonator 100 microns or less potentially. So, with that, we've actually demonstrated, here a microwave coupler operating at 5 gigahertz that, occupies a few hundred microns across, whereas doing this in normal materials, you need millimeter scale. This is the 5 millimeter scale to do the same thing. You can make integrated circuits with microwave components on them. Complex microwave components, tunable microwave components. They're tunable because of the dependence of that kinetic inductance on the charge carrier density. So, if you apply more and more current in the device, superconductivity is suppressed a little bit, still superconducts, but not quite as robustly. The superconducting gap is suppressed. As a result, there are fewer charge carriers. The charge carriers you have to go faster. Kinetic inductance goes up. This increase in kinetic inductance means that we now have a knob we can tune parametrically all of our devices. That nonlinearity, we've used it, for instance, to make this microwave resonator. We can tune it over an octave with about 100 microamps of a few hundred microamps of current in the device. Pretty good Q factor on it. And so that's one example of a utility. Okay. So what are some of the advantages of this technology? You can drive high impedance loads, turn on relatively quickly. Jitter, I think, is inferred from the jitter of the SNSPDs. It's not been measured directly except for the trons. So the H trons, we don't know exactly what it is. Has very low power consumption, not as low as traditional superconducting Josephson junction based electronics. as you can imagine, we've got a resistor in there, so it's going to be higher. It's about a factor of 100, a higher power consumption. But it's significantly slower because there's thermal effects going on. We're operating in the 100 megahertz range at best, not the 100 gigahertz range of a Josephson junction. So this is not a replacement for Josephson technology by any stretch. And you, of course, couldn't make a quantum computer out of it because it's got a resistor in it. And of course, it's also less mature than other electronics families. It's just been a few years now that we've been working on it. We have used it to make neuromorphic computers. So a simple neuron, I should say. Here's a demonstration of basically your neuronal soma is here. You've got these two prons. These are calatrons that basically allow flux to pass through, fluxoid to pass through them. And they're analogous to the sodium and the potassium channels in a cell. So we can increase the bias current, have this one fire, and we see the firing and the relaxation of these systems. And that's experimental results. We've simulated this extensively as well. We see a bunch of neuronal-like behaviors out of this. We see, for instance, you can have thresholding that depends on bias current. If you bias with only 3 microamps, there's no spike. Once you get above 3.5 microamps, you start to see spiking. You can see a refractory period. If the second pulse comes too close to the first, it gets suppressed. You can see class 1 behavior, which is as the input is increased, the spiking frequency shifts. And you can see it's called parabolic bursting, which I am told is another piece of characteristic neuronal behavior, where, you know, as you modulate the input, you see this going in and out of the threshold with these things. So they're neuron-like. In simulation, we've actually shown a number of neuronal algorithms. This is work with Nancy Lynch in the computer science department, but with her help and with a collaborator from Harvard, we showed that in simulation that you could use this system to solve a system of linear equations. So you have a matrix is equal to x times x is equal to vector. You solve for x with this, and you get a result 4, 3, 2, 1, 0. The blue one is unfortunately on the axis, and you feed that in here for x. I think it's 0, 1, 2, 3, 4, and you multiply it out. You get the result. So it's a dynamic system. You have to run it for a while for it to stabilize, but it works. All right, so back to our best theory. So where did the inspiration? I alluded at the start. This was a technology that had existed for decades. It was more than just the calotron that had existed. In fact, there was full-on working digital memories as far back as 1962 made with this technology. And before then, 1956, the device was first suggested that was used, and it was analogous to this. It was called a cryotron. It consisted of a superconducting wire and a loop. The loop created a magnetic field that suppressed the superconductivity. And Dudley Buck was the inventor of that technology. He was a professor at MIT. In fact, he was so inspired that in 1957, 1 year afterwards, they decided in collaboration with this guy, Doc Edgerton, who's famously made this photo, to bury it underground in an instant installation of a new building, and actually said that they were going to put into this time capsule one cryotron, tiny unit invented at MIT this year, which will replace complex tubes and expensive transistors in the computers of the future. So hasn't happened yet. A few years ago, MIT Nano was built at MIT. You might think it was an opportunity to put in another time capsule. You'd be wrong. Oh no, what's happening? Oh, I mean, this is going to be more fun than question and answer. So let me turn off the laser pointer. Oh, okay, just a second. We're not going to go for 6 minutes. Okay, so you guessed what it is. So that's, yeah, please do not open till 29:57. So, my graduate students, you have time. Okay. Okay. You can still achieve the, so I don't know how to get back to my talk. Does anyone, could you help me? What's that? I just don't use Macs. So I, orange icon. Thank you. This thing? Oh, right there. Okay. I see it now. Thank you. Okay, so, I just need to tab. It's still open. It's just, okay. So, yeah, so that was it was the time capsule. Thank you. Okay. We can just stay in this mode. That's fine. I'll go to full screen. Uh-oh. I'm worried about that though. Oh, good. Okay. Do not open until 29:57. I apologize for that. I was super excited when I heard about this. And because I knew what was in it. And what was in it was one of Dudley Buck's cryotrons from 1957. And I got the museum to let me in there, and they wouldn't let me open it, but they let me move it. And I sort of shook it until I got this thing out of there. And there it is. There's this cryotron, and it tells us the details of it here. But it's that magnetic winding around the wire that he used to build it. So there's a book about him. He died very young. People speculate he was poisoned by the Soviets because he was in formation and worked closely with the NSA. So if you're interested, you can look at his history. Let me just conclude there. I think I took up all my question time. I apologize, but we think this technology has potential to be useful for things. I want to emphasize this bullet point where I think there are applications in neuromorphic computing, potentially in reversible computing and other alternative computing paradigms. And I'm so happy to be here and to be able to hear what you folks think if you have ideas for how this technology might be used going forward. And with that, thank my team who worked on this. And if there's time for any questions, I'd be happy to take one.
No questions?
You mentioned resistors. Necessary, essential, like why they can reduce it?
That's actually a good point. What's really essential is that the device is pushed out of equilibrium. And so the wire, whatever it is, has to be pushed out of equilibrium. The critical current has to be suppressed. Something has to happen. From a practical point of view, if you only allow one vortex to cross the superconductor, sort of is analogous to a Josephson junction in that case. That can be achieved. We've achieved that in our work by putting a very low resistance material in contact with it. That sort of damps all of the excitation, prevents the hotspot from forming. So it's not absolutely essential, but I think at some point, as you make it less and less of an excitation, you get closer and closer to just another kind of Josephson junction. So I'm not sure.
Oliver.
Can you comment on the difficulty of fabricating nanowires compared to datas?
Yeah, thanks for that question, actually, because the point I neglected to make is that the barrier in a Josephson junction has to be controlled. And that tunnel barrier is notoriously difficult to control, whereas the wire primarily controlled by its lateral width, which is sort of the properties of it are linearly proportional to that, versus the tunnel barrier where there's an exponential dependence on it. So I think that my personal feeling is the wires are much easier to fabricate than the Josephson junctions, but because it's such a less mature technology, can't prove that to you with devices. We're just not there yet.
Correct. We can do this. Yeah. Yeah. So I wonder if you wire up those devices and make a model of a neuron, you're propagating pulse. If you look at the power consumption of a pulse and characteristics like peak voltage, threshold, and things like this, how does it compare to a biological neuron?
Yeah, it's better than a biological neurons. So if you look at this paper, journal isn't there, but it's Frontiers in Neural. Anyway, it does that calculation. So yes, but it is better than a biological neuron from that perspective.